Hi, and welcome back. Today we're going to look at the beginning of Chapter 5. This is Section 5.1, which is on polynomial functions and also inequalities. So we're going to learn about the degree, leading terms, and behavior of polynomial functions. We're going to look for real zeros of the polynomial function. And then we're going to also look a little bit at the inequalities at the end of this, at the end of these notes. So let's go through a few things about polynomials. Now, most of you have done polynomials for quite a few years in math, so hopefully this part is just review for you. A lot of terminology, so just make sure you're okay with all of that. So first off, the standard form to write a polynomial function is defined by this first equation that you see up here. F of x equals a to the n, x to the n plus a to the n minus 1, x to the n minus 1 plus, and it keeps going down until you get down to a sub 2 x squared plus a sub 1 x to the first, and then a sub 0 is a constant. Okay, there's no x variable with this term. So this looks kind of confusing, but I just want to remind you that a polynomial is very basic, where you have n that has to be a whole number. And remember, whole numbers start at 0 and go up. So your exponents have to be a whole number. So 0, 1, 2, 3, 4, 5, 6, and so forth. Okay. Then a sub n, the number out front, these are the coefficients, they just have to be any real number. Okay. So we'll get through and look at a couple of examples of polynomials. So this makes it look very confusing and hard, but remember, polynomials are very simple in nature. They're very specific on what they can and cannot have in the equation. All right, so once we get to looking at polynomials, you're going to be asked a few things. The first thing is, what is the degree of the polynomial? And that would be the largest power of n that you see in your function. Okay, so the highest power, that would be the degree of the polynomial. Then we have what is called a leading term. The leading term includes the term that has the highest power and the coefficient out front. So we label sometimes the leading coefficient with the letters LC, so that stands for leading coefficient, and that would just be the constant or the number that's in front of that x variable that has the highest power. Okay. The nice thing about all polynomials is the domain of any polynomial function is always all real numbers. And then we have to remember that polynomials are smooth functions. They don't have, or they're just smooth. Sorry, they're functions that are smooth. There's no sharp corners or cusps. They're continuous. There's no holes or asymptotes or jumps or breaks or anything. Okay, so looking at some of these pictures of graphs, this would be a polynomial. It's smooth. We can keep drawing it. There's no corners, nothing sharp on it. So this is a polynomial. These two would not be polynomials. These have breaks. It's not continuous. I'd have to pick up my pencil. It has some holes in it. It has an asymptote. This one, not a polynomial because it has a sharp curve. So that can't be a polynomial with that. So very simply, nice smooth looking graphs, which is what we've been working on for most of, this course. So these are polynomials. All right, and then the last two things, do you know how to find the y-intercept and the x-intercept? We've been doing that a lot, so these are just review. To find the y-intercept, you do f of 0. And remember, f of 0 basically means you're going to let x equal 0, and you solve for y. Okay, that's what that means right there, f of 0. So if a polynomial is in standard form, the y-intercept would also be the constant term. So you don't have to do this if you remember that last piece, which we'll talk about when we get to them. And then to find the x-intercepts, which are, remember, also called zeros and roots, solutions, there's a lot of names for the x-intercepts, you would set the function equal to 0. So this right here means you're going to let y equal 0 and solve for x. Okay, so that's just the mathematical way to say let y be 0, solve for x. This is the mathematical way to say let x be 0, solve for y. Okay? And it says, if possible, factor the polynomial and set each factor equal to 0. That's the easiest way that you're going to be able to find your x-intercepts. Okay? You could graph but most of these are factorable, so you won't have to do that if you don't want to. All right, so let's look at what makes a polynomial and not. So this is an example of a polynomial. Your exponents have to be whole numbers. So x to the fifth, x to the third, x to the first, and this is your constant term, which is really 7x to the 0, but we don't have to write x to the 0. Your coefficients, the numbers out front, those are all real numbers, okay? Real numbers could be radicals, fractions, anything. It's just the exponents have to be whole numbers. So remember, numbers 0, 1, 2, 3, 4, 5, 6, and so on. So why is this not a polynomial? A couple reasons. The first thing I would say is if I wrote this using exponents, okay, this would be 4x to the 1/2. Well, that's not a whole number, so there's one reason why that's not a polynomial. This I would write as minus 3x to the -1. -1 is not a whole number, so there's another reason why. And then lastly, I have this I right here, which is an imaginary number, so that's not a real number. Okay, so there's three things in here that are causing that not to be a polynomial, but any one of those by themselves would still make that not a polynomial. Okay. All right, so let's look at example 2. Find each of the following for this function. What's the leading term, what's the leading coefficient, and what's the degree? Now remember, typically when you write a polynomial, you write it in what we call descending order. So the highest power is always first, and then it descends by power. But in math class, a lot of times they mix these up just to see if you're paying attention. So even though the highest power should be the first term, you always want to check all the other terms and make sure, you know, they're not mixing those up on you. So in this case, this is definitely the highest power, x to the fifth. So that is our leading term. So just because it says leading term doesn't mean it's going to be the first one. It's the one with the highest power. Okay? All right. So, you know, if I wrote this problem as 8x cubed minus 4x plus 2x to the fifth plus 7, let's say I wrote it that way. It's the same polynomial. This is still the leading term. Okay? The leading term is the one that has the highest power associated with it. All right, so then once you find the leading term, these two come right from this. So the leading coefficient is the number in front of the variable, and the degree would be the exponent that you have in that problem, okay? We'll do some more of those coming up. All right, now underneath here are just some of the polynomials that we've done already in here. So we've had, you know, f of x equals 0. That's just a horizontal line that goes through 0. It doesn't have a degree. That's x to the 0 power. Okay. If you have a function f of x equals a number, like f of x equals, in this case, it looks like 1, 2. Okay. So that would be the graph f of x equals 2. That's a constant, but it's still a polynomial. Again, that's x to the 0, so that would be okay. Then we've done linear equations, right? The y equals mx plus b. They're just using a and b here instead, but we've done those. We've done quadratics, okay? Start with x squared, so that's the highest power. And then we've done cubic functions, which we're going to get some more of, but we did the parent functions of that. So ax to the third, right? That would be the highest power. So they go on, x to the fourth, x to the fifth. So a polynomial function can have a real high power as long as it's a whole number. It would still be considered a polynomial, okay? So those are just ones that we've worked on already. So let's look at some other things about polynomials. So it says that a polynomial function that has real zeros may be written either in standard form or in factored form. So you have to be able to work with both in this section. So let's go ahead and factor this first, and then we'll talk about how do you get these answers based on, you know, which form that you have, okay? So if I want to factor this, the first thing I want to look for is a greatest common factor, and I never want my first term to be negative. So I'm going to factor out a common factor between 6, 26, and 28 would be 2. But I want to factor out a negative 2, okay? And then I also have x's that they have in common, so I would also factor out an x squared. So I'm going to factor out a negative 2x squared. All of those have that in common. and I'm going to take negative 2x squared and divide it into each of these terms and write down what's left in the parentheses. So if I divide negative 6x to the fourth by negative 2x squared, I'd end up with 3x squared. If I divide 26x cubed by negative 2x squared, I'm going to end up with a negative 13x. And if I divide the last term, negative 28x squared by negative 2x squared, I'd be left with a positive 14. And then I could keep factoring. That's a trinomial that will factor. Okay, so it factors into two binomials. So remember, the first two terms have to multiply to give you 3x squared. So that has to be 3x and x. Then I have to figure out whether I'm going to use 1 times 14 or 2 times 7 to get my 14. And remember, we do that by trying to get 13 in the middle. So I am going to do 7 here and 2 there, because the inside would be 7x and the outside would be 6x, and 7 and 6 is 13. And they need to be negative, right? That gives me the negative 13, and it also gives me a positive 14 if I multiply them. So there's my factored form, okay? So they look a lot different, same problem. So obviously, to do the leading term, the leading coefficient, and the degree, this is the easiest way, okay? So the leading term, highest power, would be negative 6x to the fourth. Leading coefficient would be negative 6, and the degree would be 4. Now, if you have a problem this way, which we're going to do a few in a minute, but let's just say you don't have this over here, okay? This is not here, and you're asked these questions, and where do I get those from here? So when you're asked about the leading term over here and it's in factored form, you would take each of the first pieces of each term and multiply them together. So if I wanted to do the leading term over here, I would take negative 2x squared, multiply it by 3x, and I would also multiply by x. So I'm taking each of the first parts of those, and if you multiply that out, negative 2 times 3 is negative 6, and then remember you add your exponents, so 2, 3, 4, that gives you this right here, okay? So a little bit harder to do here, but it's definitely doable. So just remember, you take the beginnings of each factor and multiply those together. All right, so let's talk about end behaviors now. So power functions and end behaviors. So when you look at each term of a polynomial, they're each called their own power function. Okay, so if I'm looking up here, negative 6x to the fourth is its own power function. 26x cubed is a power function. You put them all together, they become a polynomial. Okay, so the end behavior of a graph of any polynomial function will be the same general shape as the graph of its leading term. Okay, general, not specific. Okay. So again, we need that leading term to figure out a lot of stuff with polynomials. That's why we were asking you to find the leading term in the last few pages, okay? All right, so here's a picture. A lot of you guys are visual, so I think this helps, but we're also going to talk about the left side and the right side. So going back to our pictures over here, look at these bottom two. So this is your basic quadratic function. So because it's x squared, notice that both sides go in the same direction. I'd call this the left side and it's going up, and I would call this the right side of the graph. It's also going up, okay? Notice on a cubic function, the right side goes up, but the left side goes down. So they're doing opposite things. So what we're getting ready to do is figure out how we know what the left and the right side of an equation does based on the leading term, okay? So I like to use left side, right side, and I use the arrows. I use the pictures, but if you're working in Hawks, then a lot of times they're going to ask you the sun, like where is it going? So instead of saying up, that would be the same thing as positive infinity. And this side would also be going up, which is positive infinity. This one would be going up, positive infinity, and then this one, since it's going down, anything that goes down would be negative infinity. So when I say up or the right arrow, you know, it's going up, then that's a positive infinity, and going down, that would mean negative infinity, okay? All right, so there's only 4 possibilities. So the first thing you're going to look at, is, I think, would be the leading coefficient, okay? The leading coefficient is positive, then that means the right side goes up, okay? If the degree is even, that's telling you that both ends are going to do the same thing. Okay, so if the degree is even, either both sides are going to go up or both sides are going to go down. So that's these two pictures here. So the way that you know what happens is by looking at the leading coefficient, okay? So if the leading coefficient is positive, right side goes up. And if the leading coefficient is negative, then the right side is down. Okay? Sorry, I don't have a lot of room there. The right side goes down. Okay. Then, basically the same thing. This never changes. So if the leading coefficient is positive, then right side up. And if the leading coefficient is negative, right side down. So I always look at that first because I want to know what the right side's doing. Then I'm going to look at the degree. If the degree is odd, then the ends do the opposite thing. Okay, so just remember, odd, opposite, that kind of makes sense. Even means everything's kind of the same, right? Even, so that would, they'd be doing the same thing. Okay, all right. So with that in mind, let's look at example 4. Use the end behavior of this graph to determine whether the degree is even or odd and whether the leading coefficient is positive or negative. All right, so remember, I always look at the right side first. So in this problem, since the right side is down, right side's going down towards negative infinity, then that means the leading coefficient is negative. Okay? And then since the two ends are doing the opposite direction, that means the leading term is odd, has an odd exponent. Okay, odd, I'll put exponent there. So what this tells me is the leading coefficient is a negative number and the exponent has to be odd. Okay, so that's for this one. For part B, since the right side is up, okay, right side up, that means the leading coefficient is positive. I didn't want to put that there, it was a negative, so we'll just make that a hyphen. Okay, so right side up, the leading coefficient has to be positive. Right side down, the leading coefficient has to be negative. Now, since both ends are doing the same, going in the same direction, that means that your exponent, the leading term, has to be even. Okay, so that tells you a lot about the function just by looking at the shape or the arrows or which way it's going. Now, we can do the same thing if we're given an equation. How do you know what the ends are doing? So let's look at that. All right, so look at example 5. This one, if we're given the function, let's state the direction of the left and right end behaviors. So I like this because I just draw the arrows, okay? So state the direction of the left and right end behaviors. All right, so we need the leading term. So I'm going to circle that. Highest power, leading term, leading term, leading term. So this one, they're given to you all in the right order. So your leading term is the highest power, okay? All right, so look at the leading coefficient. Leading coefficient is positive. And the exponent, I'm going to say the degree, sorry about that. The degree, that's the highest exponent, is odd, right? All right, so positive coefficient means right side goes up. So I draw an arrow on the right side going up. And since the degree is odd, that means this other side's going to do the opposite thing. So this would be right side up, left side down. Okay. Again, in Hawks, this would be going to positive infinity, the right side. The left side would be going to negative infinity. All right, let's look at part B. We got the leading coefficient first, which is positive. It's a 1. All right, these were both 1s. But this time the degree is even. So again, the leading coefficient, you always start with the right side. So it's going up because that's positive. Since the degree is even, that tells you the left side will also be going up in the same direction. All right, and lastly, negative 3x to the 5th. So this leading coefficient is a negative number. And the exponent, the degree, is 5, which is odd. So this one, since the leading coefficient is negative, right side has to go down. And since the degree is odd, they have to be doing opposite things. So the left side would have to go up. Okay? So just the leading term tells us about those end behaviors, what's happening. Now the rest of the graph is going to tell us what's going on in between those arrows, but that tells us what we need to know to begin with. All right, look at examples 6 and 7. Determine the leading term and the end behavior of the following. So here's one that's not factored. This is standard form, and here's one that is factored. Okay, so on this one, it's easy. The leading term is right there. So the leading term is negative 2x to the 5th. The end behavior, what's going to happen? Negative leading coefficient, right side down. Odd exponent for the leading term, so that means both sides have to be doing different things. So the left side would be going up. All right, now here's a good one about what we talked about. When you have the factors, you got to take the leading term for each factor. And here's a good example because we have these exponents here. Okay, so watch what I do carefully on this one. So we're going to take each of the first terms. So negative 7. We got x squared. Now, you're not just going to multiply x here because it's not really x. Remember, you got to FOIL this out. So the first term is really going to be x squared. So you have to take into consideration that exponent. And then this last term, same thing. You're not just going to use x here, but it would be x to the 6th. So don't forget about the exponents outside. The first one we didn't have any. Okay, go back to that real quick. Okay, this one that we did earlier, when I took the first terms, there were no exponents here. They were just 1. So that's why I just took those. But you do have to take into consideration. So now I would multiply all that together. So negative 7 is the only number I have. Times 1 times 1 times 1 is negative 7. And then you add your exponents. So 2 plus 2 plus 6, that would be x to the 10th. So there's your leading term. So your end behavior, first and foremost, I go to the leading coefficient, which is negative. So the right side has to go down. And since my degree is even, the left side also has to go down. Okay? Again, this goes to negative infinity. This goes to negative infinity. This side, right side would be negative infinity. That would be going up. So the left side would be going up to positive infinity. Okay, so I just use the arrows, but you can change that quite easily if you're on Hawk's working mode.